We're going to discuss what limits are and attempt to improve your understanding. So let's try to get started. We'll try to draw an image. Here is an image. This is the XY plane. We're going to draw the graph of a function. This function is may look somewhat contrived, but there's a method to this madness. What you have here is we're going to have y equals f of x. It's equal to, we have x squared. We're going to jack it up 1 unit, push it up 1 unit, translated vertically 1 unit, x squared up 1 unit when x is not 0. And we're going to call it 2 when x is equal to 0. When x is equal to 0. Now, this is a real valued function of one real variable. So we want to discuss what the possible answers are to this question. What are the possible answers to this question? What's the limit as x goes to 0 of this function? And so here's some popular answers. One answer could be that it does not exist. Does not exist. That's a mathese for does not exist. Or the answer might be 2. Or the answer might be 1. So you can take your choice here. Maybe it does not exist because you see a hole there in the graph. It's kind of exaggerated since it has no length or width. So maybe you think it doesn't exist since it's not defined. It's jumping away. Well, this is wrong. We'll discuss it later. Maybe you think the answer is 2. Well, 2 is f of 0 is 2, but this function is not continuous. Is a jump, a gap in the curve, and if it was a continuously drawn curve there, then the answer would be 2 if the curve approached 2, because approached is a very key word. There's a limit is an approach. What's the approach? The approach is as x goes to 0, we have put this little man here. I don't know if he's happy or sad, but his little man is heading towards the origin, which is the limit point. As he heads towards the origin, the y value approaches 1. Looking up at the curve, these heights are going to 1. And this guy here, his shadow man is more pleased. Shadow man also sees from this direction, the y value is also approaching 1. So that's your winner. Your winner is 1. Now, if you chose A or B, Means you don't really understand what limits are, okay? Yeah. So now I'll try to do an example to edify you as to what limits might be. There's an illusion of motion there, approaching from the negative side and the positive side. But in fact, the limit is already it already has been taken. It already exists. You're computing it, and the illusion of motion comes when you're doing the computation, when you're trying to find out what it is. Now we have an example. Here's your example. We want to limits extend ideas. In calculus, you have the idea of area. Area is, you can extend it from figures bounded by line segments, can be extended to figures enclosed by curves. This is you figures bounded by line segments, like rectangles and triangles. Okay, you have rectangles and you have triangles. We know how to find those in pre-calculus, and then figures enclosed by curves, not so much. Not so much figures enclosed by curves. So we're gonna give an example of this extension. All right. Now, what we do know is that circles are similar figures. We have one circle here. Here's your diameter of this circle, and here's the circumference of this circle. This is your diameter, and there's your circumference. Now, if I have a big circle, I have here is your diameter, and there's your circumference. Okay, there's your circumference. Now, the truth of the matter is that the ratio of C over D is the same in both the little circle and the big circle. I'm sure that you don't really doubt that. In fact, C is about 3 times as long as D. But the actual ratio is, we use this letter, Greek letter, pi. Pi is a constant. A ratio of C over D is a constant. Okay. So those are things that you discuss in pre-calculus without really proving this equality here. But C is pi times D. So we can erase that. And what we want to do is extend the idea of area to circles. So we're going to prove the one formula for area. Now, how do we do that? Well, we can do this. We can circumscribe this circle with regular with regular polygons. This is a hexagon, or we could take more sides of it, regular polygons. So now we can split up the regular hexagon into triangles. Now, what would the height of the triangle be? Well, we don't. Before we do that, we have the base times height divided by 2 is the formula for the area of a triangle. So here's the base. So we have the area of a regular n-gon, n sides, a regular circumscribed n-gon. Well, one thing to notice is that what's the height, what's the altitude drawn here to this base? It's going to be the radius of the circle, right? I mean, so the formula here would be 1/2 base times height plus 1/2 base times height plus 1/2 base times height. That would be n times. Now, as we take more and more sides of these, if we can circumscribe like 100 gon, 10,000 gon, and what happens is that we actually do get closer to the area, which I don't have to prove, but I'm gonna just assume it. We're going to get closer to that area as we take the limit. You take the limit as n goes to infinity. That's going to be the limit as n goes to infinity. Okay. Now, what's happening to the r's and the half? They're not changing. So we can factor them out. What about the b's? Well, the b's are going to what? 0. Each base is getting smaller as you get more and more sides. However, the sum of the b's, what's happening to them? Well, the sum of the b's actually are going to the circumference. So b's are, when you add them all up, they're getting smaller, but the sum is approaching the circumference. We don't care about when they go to zero, when they are at zero, when the bees are at zero. We're just approaching. So we get here, we get 1/2 R times C, 1/2 R times C. But that's going to be the area of the circle. So the area, formula for the area of the circle is 1/2 R times C, with C, as we said before, is pi times D. But D is twice the radius. And these twos are going to cancel and we get pi r squared. So there is your example of taking a limit and extending the idea. You can think of a circle as a regular polygon with infinitely many sides, but it's not a polygon because the limit took you out of the domain of polygons and into the domains of curves. Okay, and that's the name of that tune.